Hi everybody, welcome back to Climate Change Calculated. Today number 8 about energy storage. My name is Gerald Schuller. So let's start with the United Nations 2030 climate goals, which you can see here on this website. So let me start by opening it. So here's this website, and here you can see what the goal would be. So to limit the global warming to 1.5 C above pre-industrial levels, emissions must already be decreasing and need to be cut by almost half by 2030. And that's just 7 years away. So that's a lot. So cut by half by 2030. So this should be the goal. So the goal should be to have a future economy and technology without fossil energy. So let's start with an outlook until 2030. So the question is, what happens if it is dark and we do not have enough wind? The conventional answer would be we need gas peaker plants which generate electricity when needed, but that again is fossil fuel. So the better answer would be we need electricity storage. So the question then is that doable? So let's check it. For renewable energy, storage is needed. And the Fraunhofer Institute, ISE, actually looked into it. And they found this, let's take a look at the website here. So that's their website. And they found Germany has an installed capacity for storage in 2021 of approximately 750 megawatt hours. But the total storage demand in Germany by 2030 would be 104 gigawatt hours, so a lot more. And in 2045 it would be 180 gigawatt hours, of which large-scale battery storage can cover a significant share. So the battery storage here is actually the key. So let's take a look at it. So for the battery storage, an important property is the levelized cost of storage, short LCOS. And I found this paper projecting the future levelized cost of electricity storage technologies from January 2019. So and this paper says the total lifetime cost of the definition of LCOS is the total lifetime cost of the investment in an electricity storage technology divided by its cumulative delivered electricity. So this includes the price for the stored electricity. Hence, this can be seen as the price a storage owner can sell the electricity without making the profits. So that's the basic definition. And the paper then, the highlights are that it shows the lifetime cost for 9 storage technologies and 12 applications from 2015 to 2050. So it shows the development of those costs. Yeah, it also shows the lowest lifetime costs fall by 36% by 2030 and 53% by 2050. So we can expect a big drop in expenses and cost across the shown 12 applications. And it also is shown that lithium ion batteries are the most competitive in a majority of applications from 2030. And that's to a good part coming from the improvements in battery manufacturers, for a good part driven by electric cars. There's also pumped hydro. So this is what we had so far, that we had lakes on mountains for storage. Then we have compressed air, hydrogen, and these are best for long discharge applications, like from summer to winter, for instance. Yeah, so now let's take a look at the cost in cent per kilowatt hour or dollar per megawatt hour. So here we can download the figures from this paper. And the most interesting part here is the 4 plots down here. And you can see here this the one before the last, this lithium ion. And here you can see the time scale, 2015 to 2050. And vertically is the LCOS in US dollar, the 2018 dollars per megawatt hour. And you can see the bars here show the range of cost or prices. And you can see on average there's this exponential decline of cost, and you can see it's already close to 200. So soon the average will be below $200 per megawatt hour. You can see here pumped hydro is a little bit higher. Flywheel is actually a lot more expensive, so this is for very short duration. And here redox flow batteries, these are batteries with fluids, often used for more long-term storage. Yeah, so let's take a look at what this means. So $1 per megawatt hour is 100 cents per 1,000 kilowatt hours, which is 0.1 cents per megawatt hour. So the assumed electricity cost is $50 per megawatt hour, or 5 cents per kilowatt hour, which is the producer price here. So after 2025, from this graph, we can see that lithium ion storage will be below $200 per megawatt hour, or 20 cents per kilowatt hour. And without the assumed electricity cost of these 5 cents per kilowatt hour, that means pure storage is just 15 cents per kilowatt hour. When we compare LCOS, then pumped hydro is slightly higher, 25.9 cents per kilowatt hour. Flywheel is a lot higher at 44. We actually find similar values here in this link, in this publication. So the numbers agree. Yeah, so the result here is we see that lithium ion batteries will be among the cheapest storage option, and the cost of storage approaches 15 cents per kilowatt hour. Yeah, and we already have an example, the Tesla Megapack. So we can take, there's actually this report, and that says that the production of the Tesla Megapack is to reach 40 gigawatt hours of annual production capacity, and many more mega factories would be coming. So this is ramping up, for instance in Shanghai. Hence a mega factory, one factory with 40 gigawatt hours of annual production, could cover the total storage demand in Germany by 2030 of 104 gigawatt hours in just about 2.6 years. So it's doable. The production capacity is ramping up, and with this ramped up capacity, it's actually quite realistic to satisfy the storage demand. Yeah, and then we can actually take a look at the order page of the Tesla Megapack. So we can take a look by clicking on it. So here you can see this Megapack. It's actually not too big. It's like a big cabinet. And this features 9.6 megawatts of power and 19.3 megawatt hours of stored energy. Here you can see duration. So this basically is the rated power that it can deliver. So here it takes 2 hours to discharge this battery. We can also switch to 4 hours. Then we have a reduced power here, which makes it somewhat cheaper. But let's go back to the 2-hour one. And here you can see the estimated price. It's a little below $10 million. So that sounds a lot, but let's calculate the price of storage. We also have an estimated annual maintenance of $29,000, but that can be neglected compared to the purchase price. Okay, so now we have numbers. So taking this price and the capacity, we can calculate this is $517 per kilowatt hours. And let's see what that means. But before we can calculate the cost of storage, we need to know how long does the battery last. So we need to know the number of equivalent full charging cycles for these lithium-ion batteries to calculate how long they will last. And for that I found this dissertation from Peter Keil from Technical University of Munich. And it has actually quite an interesting plot on page 127 for long-term cycling, which is figure 88. So let's take a look here. This is this figure 88. And here on the left-hand side, you can see on the x-axis the equivalent full cycles. So one full cycle is basically corresponding to a full charge and discharge of the battery. If it's only half charged and discharged, then it's a half cycle. And here you can see the relative capacity. So when it's new, we have the relative capacity of 1. And then you can see over time, over the number of full cycles, the capacity fades, it goes down. But actually not that much. So you can see here in the worst case, it goes down to about 0.8. The other cases are actually better. The dashed lines here correspond to the case when the battery is just sitting there idly without being charged and discharged. So there's also a slight loss of capacity, but not much. So here basically we can assume this 0.8. So after 2000 cycles, we still have 80% of the capacity left, which is actually quite good. So for stationary storage, 80% is more than enough. So I assume it's still usable until the capacity is down to 51%. And that means about 6,000 cycles. So 6,000 cycles is 3 times the 2,000 cycles. And that means we have 80% of 80% of 80%. So 0.8 to the power of 3. And then that's how we get to 51% capacity left after 6,000 cycles. So we can now compute with those 6,000 cycles. Yeah, so also to compute the cost of storage, we need to take into account that not all electricity is returned, some is lost. So in general, you can say about 85 to 95% is returned. So roughly 10% of the electricity is lost, which is about 0.5 cents per kilowatt hour. So that has to be added to the cost of storage. Yeah, and then we can also assume the average capacity over the lifespan, which is between 100% and 50% at the end of the life. So 75% would be roughly the average. So we take the 75% to calculate the cost of storage. So then we have 75%, so 0.75 times the 19.3 megawatt hours is then 14.475 megawatt hours on average. And then we can compute the cost of storage without the maintenance cost to this roughly 10 million, and then we divide it by the total electricity that we can actually get out of it. 6,000 full cycles times this total capacity plus the 0.5 cents electricity loss. And that results in this 11.5 cents per kilowatt hour. So this is already at or below the price range predicted for 2030. So it's actually quite good. Yeah, when we add the above assumed price of electricity to the cost of storage, then we get LCOS back. So here 11.5 plus 5 cents is this 16.5 cents per kilowatt hour. And that's roughly what we saw in the prediction before. Yeah, now we can compare to the alternative, the previous alternative, the gas peaker plants, which we want to replace. So we want to know, what does it cost, right? We have gas peaker plants, they cost something, and batteries, they also cost something. And here in this Wikipedia page, I actually found an estimate for 2020, which is 15 to 20 cents per kilowatt hour from gas peaker plants. And when we now compare this, it's similar to that of the cost of storage. So we have 16.5 cents per kilowatt hour for our battery storage, the Tesla Megapack. But this price is likely to go down, but the gas peaker plant price is likely to go up because gas is becoming more expensive, and also to build new gas peaker plants, which only are active very short times, makes them also more expensive. So it can be predicted that soon batteries will be much cheaper than gas peaker plants. So also they have quite a small form factor, so the batteries could actually replace gas peaker plants in which they could be installed. So we could take the existing old gas peaker plants, take out what they have inside and just put the batteries there. So there are actually many examples in the world. Well known is this here in Moss Landing in California. So let's see if we can see it here. Yeah, so this is the Moss Landing battery storage project, where basically they took this gas power plant and put batteries inside, and basically used the entire infrastructure, meaning the cables, the connection to the power grid, and just put batteries inside. So this is very cost effective in this way. It also doesn't cost any more space. So very practical. So in conclusions, electric grid storage with batteries has a cost comparable or lower than gas peaker plants. Grid storage with batteries is doable, relatively cheap, and the technology is there or will be there soon. Grid storage thus enables complete decarbonization of electricity generation. So we can have just, for instance, wind and solar, and just use grid storage to buffer the generation. And it just needs to be done. The technology is there or ramping up. So we just need to plan accordingly, taking into account the newly developing technologies. Okay, so I think that's quite a nice outlook. So with that, thanks for your attention, and then see you next time. Bye-bye.